So we continue with our discussion of continuous functions with a discussion of some properties and rules for continuous functions. So first rule, sum of continuous functions. If f and g are continuous at x equals x naught, then f plus g is continuous at x is equal to x naught. So for example, f is continuous everywhere, and c is continuous everywhere. So the function x plus c is continuous everywhere. A difference of continuous functions. If f is continuous at x equals x naught, and g is also continuous at x equals x naught, then the difference, f minus g, is continuous at x equals x naught. So for example, I have that x is continuous everywhere and c is continuous everywhere, so x minus c is continuous everywhere. Scalar multiples. If f is continuous at x equals x naught, and c is an element of the reals, then the scalar multiple of f, c times f, is continuous at x equals x naught. For example, x is continuous everywhere, and if a is a real number, then the new function ax is continuous everywhere. Continuing with that example, if ax is continuous everywhere and the constant function b is continuous everywhere, so ax plus b is continuous everywhere, right? Monomials are continuous everywhere. Products of continuous functions. If f is continuous at x equals x naught and g is continuous at x equals x naught, then the product f times g is continuous at x equals x naught. So for example, x is continuous everywhere, and x is continuous everywhere. So x times x, which equals x squared, is continuous everywhere. Now, if x squared is continuous everywhere, and x is continuous everywhere, then x cubed is continuous everywhere, and so on and so forth. All x to the n for n is a positive integer are continuous everywhere. Now, if x to the n is continuous everywhere for n a positive integer, and we can take scalar multiples also of a n x to the n, those will be continuous everywhere, and then we add those up in sums, then polynomials are continuous everywhere. Quotients of continuous functions. Have to be a little bit careful when you're dividing. You don't want to divide by 0. So if f is continuous at x equals x naught, and g is continuous at x equals x naught, then f divided by g, the new function f divided by g, is continuous at x equals x naught, provided that g of x naught is not equal to 0. Okay? So let's take an example. Sine and cosine are continuous everywhere. So the tangent is the quotient of those two continuous functions. Tangent equals sine over cos. So it will be continuous everywhere except when the cosine takes the value 0. Okay? So tangent is not continuous everywhere. Tangent is continuous wherever it is defined. Okay? Composition, if you have composition of continuous functions, so f is continuous at x naught and g is continuous at f of x naught, then g composed with f is continuous at x naught. So for example, here we have a function. So we have a polynomial function, 1 plus x squared. Then we compose it with the sine function. So sine of 1 plus x squared. So this is the composition of functions which are continuous everywhere. So sine of 1 plus x squared is continuous everywhere. Now, 1 plus x squared is continuous everywhere, so we have the quotient of a function which is continuous everywhere divided by a function which is continuous everywhere. So this function, f, is continuous everywhere. Now, how would you prove these properties? Well, what you do is use the related properties of limits and check the three definitions. Okay. Let's consider this one. F sends reals except for 0 to the reals, defined by sine of 1 over x divided by x. So let's think about it for a minute. 1 over x is continuous everywhere except at 0. Okay? And sine is continuous everywhere. So if we take the composition of these functions on the reals, except for x is equal to 0, then that function is continuous everywhere on its domain. And 1 over x is continuous everywhere on the domain R except for 0. So the quotient is continuous everywhere on the domain R with 0 removed. Okay, another important class of functions are the rational functions. These are of the form p over q, where p and q are polynomial functions. Where would these be continuous? Well, they would. It's the quotient of functions, which are continuous everywhere. So they are continuous everywhere except when q takes the value 0. Okay. How about this one? Well, sine is continuous everywhere, and it's being composed with a function which is a quotient of functions. So the numerator function is continuous everywhere. The denominator function is continuous everywhere. So this quotient will be continuous everywhere except when cosine is equal to -1. And so the composition will be continuous everywhere except when cosine is equal to -1. Now, once again, there are some functions which are continuous on all real numbers, polynomial, constant functions, polynomials, sine, cos, and exponential. So these are important properties to keep in mind.